Imagine building the most powerful database in the world, locking it inside a giant vault, and then just throwing away the key. That's exactly what an isolated database is. It's completely useless if users can't actually get to the data. Welcome to our explainer on database connectivity and web technologies. Today, we're unpacking Chapter 15 of our software engineering material, and we are going to learn exactly how we build that absolutely crucial bridge between our front-end application programs and our back-end databases. Think of this connectivity as the central nervous system of modern software architecture. Okay, let's dive right into this. Here is our roadmap for the session. We're going to start by defining database middleware. Then, we'll decode the alphabet soup of connectivity tools, explore the shift to web-to-database middleware, look at XML and cloud computing, and finally, wrap the whole thing up with a solid exam prep summary. Let's kick things off with Section 1, an introduction to database middleware. So to solve that locked vault problem we talked about, we need something called database middleware. By definition, this is the connectivity software through which application programs connect and communicate with data repositories. You can think of it like a highly skilled translator bridging the gap between two people who speak completely different languages. It's the software sitting right in the middle, taking your application requests, translating them into a format the database management system understands, and then safely returning the data back to you. Now, to actually interact with this middleware, programmers use what we call an API, an application programming interface. An API is essentially a set of software routines, protocols, and tools. A really good API provides all the necessary building blocks, so a programmer doesn't have to reinvent the wheel every single time. They just want to pull a simple list of names from a table. They just use generic API commands, and the middleware handles all of the complex database-specific routing behind the scenes. Moving right along to Section 2, let's untangle what we like to call the alphabet soup of connectivity. Looking at the history of Microsoft's connectivity tools can honestly feel like staring into a bowl of alphabet soup. There are acronyms everywhere. But let's track how this architecture evolved. In the early 90s, things kicked off with ODBC. By the mid-90s, the industry needed a lot more power, which led to OLE-DB. And then, from the 2000s onwards, we enter the modern era, with frameworks like ADO.NET and JDBC. Let's break those down a bit. ODBC stands for Open Database Connectivity, and it was truly revolutionary at the time. It was the original standard API that allowed Windows applications to access relational data sources using SQL. However, it had a catch. It was limited purely to relational data. As programming evolved, developers needed better, more specialized access methods. This limitation forced the creation of DAO, or Data Access Objects, which were optimized for desktop databases like MS Access. Around the same time, we got RDO, or Remote Data Objects, which were designed to handle heavier, server-based databases. But, the real underlying problem was still non-relational data. How do we access that? To solve this, Microsoft created OLE-DB, which stands for Object Linking and Embedding for Database. This was a massive leap forward. Based on something called the Component Object Model, or COM, OLE-DB added object-oriented functionality, allowing us to access both relational and non-relational data. It elegantly divided its architecture into two types of objects: consumers, which are simply the applications that request the data, and providers, which are the objects that actually deliver that data. Now, OLE-DB was incredibly powerful, for sure, but it was also incredibly complex to work with. So developers brought in the next layer, ActiveX Data Objects, or ADO. ADO was built right on top of OLE-DB to provide a beautifully unified, simplified interface. Instead of wrestling with complex code, programmers could use simple objects. For example, you'd use a command object to execute your queries and a record set object to hold the returned data. It made the programmer's life significantly easier. And that evolution leads us directly into the modern Microsoft framework, ADO.NET. The really fascinating concept to grasp here is the data set. This represents a fundamental paradigm shift in how we handle data. A data set is a disconnected, memory-resident representation of the database. What does that mean? It means the application pulls the data, stores it locally in XML format, and then completely disconnects from the database server. You can work entirely offline, make your changes, and then synchronize everything later. For the modern, distributed internet, this disconnected model is an absolute game changer. Stepping away from Microsoft's ecosystem for just a moment, we have to talk about Oracle's equivalent, Java Database Connectivity, or JDBC. Now, Java's entire philosophy is built around a write-once, run-anywhere environment. To pull this off, JDBC uses a portable applet architecture, meaning the Java code runs safely inside a secure virtual machine on the host computer. The massive advantage here, JDBC requires absolutely no client-side configuration. The database driver is automatically downloaded as part of the Java applet, which allows for totally seamless cross-platform connections. Let's shift gears now into Section 3, Web-to-Database Middleware. So far, we've mostly been talking about traditional desktop application connectivity, but when we transition our focus to web browsers, an entirely new set of challenges arises. Integrating web technologies gives us amazing benefits, like location independence, meaning you can access your data globally from any smart device, and incredibly rapid development. But this global, web-based architecture comes with a rather massive technical hurdle. That hurdle is the fact that the web is inherently a stateless system. This is absolutely crucial to understand. A stateless system means the web server does not maintain an open communication state with your browser. The very second it sends you a web page, it completely forgets who you are and severs the connection. Which brings us to the ultimate puzzle of this section. How on earth does a stateless web browser, which only understands HTML, speak SQL to a backend database? Remember, the browser and the database speak completely different languages, and the web server sitting in the middle drops the connection the second the page is loaded. The elegant answer to this problem is a server-side extension. This is a program acting directly as Web-to-Database Middleware. Scripts written in languages like PHP, ColdFusion, or ASP.NET act as the crucial translator here. The server-side extension sits right alongside the web server. It provides the specific functionality needed to understand what the user wants, write the correct SQL query, and then talk directly to the database. Let's actually walk through the steps and mentally map the exact journey of a single mouse click. Step 1. Your browser requests a web page. Step 2. The web server receives that request, realizes it needs database data, and passes the script over to the middleware. Step 3. The middleware reads the script, connects to the database using an API, and executes the SQL query. Step 4. The database returns the raw data to the middleware, which then dynamically wraps those query results in HTML formatting, passes it back to the web server, and finally it renders beautifully on your screen. That brings us to Section 4, XML and cloud computing. Now we need to introduce the final pieces of our modern connectivity puzzle, how we universally format all this data, and where we actually host the infrastructure. The core concept here is understanding the difference between HTML and XML. HTML is solely concerned with how data looks, the fonts, the colors, the layouts. XML, on the other hand, describes what the data actually means. Extensible Markup Language lets businesses define their own custom tags, like a specific tag for product price, to exchange data seamlessly between businesses. To make sure everyone is playing by the same rules, we use document type definitions, or DTDs, and XML schemas to rigorously validate that the XML structure is correct. And where does all this incredibly structured data live today? Increasingly, it lives in the cloud. Cloud computing is the ultimate modern data repository. It's a computing model that provides ubiquitous, on-demand access to a shared pool of configurable resources. Think networks, servers, storage, and applications. The real beauty of the cloud is that it completely removes the need for companies to buy and maintain expensive on-premise hardware, allowing resources to be rapidly provisioned with very minimal management effort. When we talk about cloud services, they generally fall into 3 pay-as-you-go models. First, we have software as a service, or SaaS. These are turnkey, ready-to-use applications like SQL Data Services or Microsoft Office 365. Second is platform as a service, or PaaS. This provides a framework so developers can build their own custom applications without ever having to worry about configuring the underlying operating system. And finally, infrastructure as a service, or IaaS, which is quite literally just renting raw computing power, storage, and networking hardware over the internet. Let's wrap things up with Section 5, our summary and exam prep. We have covered a vast amount of ground today, traversing decades of software engineering history. Consider these key takeaways your ultimate cheat sheet for the exam. Remember, middleware is the essential translator bridging applications and databases. ODBC was the original API standard for SQL. ADO.NET revolutionized things with the disconnected memory-resident dataset. You must remember that the web is fundamentally a stateless system, which is why it absolutely requires server-side extensions to act as web-to-database translators. And finally, while HTML formats how things look, XML gives meaning to our data for seamless, universal exchange. I want to leave you with one final provocative thought. Today, we've learned the mechanics of how to connect applications to data, how to pull it into disconnected XML datasets, and how to host it all dynamically in the cloud. But as all of this sensitive data travels openly across the internet, how on earth do we protect it? How do we secure these massive cloud-based repositories against incredibly sophisticated modern cyber threats? Well, that exact question leads us directly into our next module, database administration and security. Thank you so much for joining me today, and I look forward to exploring that with you next time.